have the great honor of actually of presenting to you my undergraduate mentor, Professor Alexander Migdal, who was there at Princeton and taught me so many things and obviously inspired me so much to do mathematical physics, primarily by the philosophy of pure suffering and suffering purification that I'm still doing this thing. So I have the great honor of presenting to you Professor Migdal, who is now at NYU, having taken 20 years off to make multiple billions, I think.
Oh, no, no, no. Just to have fun.
Just to have fun. Okay.
You know, billions were not achievable. It was a pretext to do some different kind of science.
Okay.
But fun was there, yes.
I'm sure it was. So I'll present you. Professor Migdal is going to talk us about some of his recent works on vortices and Navier-Stokes.
Thank you. It's my pleasure to talk at this symposium. I have greatest respect to topology and Professor Chern. And part of what I'm going to be talking about is related to topology. And maybe it's more related, I just don't know yet, because the whole field is moving very fast. Anyway, I'm going to talk about vortex sheets and turbulence statistics. And my goal is quite ambitious. I'm trying to explain and quantify the main properties of the turbulent flow. And let me present what I have. And it's, of course, for other people to judge whether that indeed explains things. But so I'm going to present it. So we found an attractor in Navier-Stokes equation, a 9-dimensional fixed point, which we call CVS, parameterized by Gaussian random strain matrix, random position vector, and random scale factor. Attractor is a stable fixed point, which you approach that stable fixed point regardless of initial conditions while they're in some range, like fast-moving torpedo in the water, that kind of thing. So there is a attractor which could explain main features of the turbulent flow. Irreversibility, which is the most puzzling feature, that follows by stability of this solution. Turns out that microscopic stability of the vortex surface, which is part of that solution, only exists, and it requires negative strain in the normal direction to the surface. That's a new requirement. And since strain is a time-odd quantity, so requirement of negative strain fixes the direction of time, and that leads to irreversibility. And the problem, of course, with irreversibility was that in the limit of zero viscosity, which is the turbulent limit, you formally could neglect diffusion in the Navier-Stokes, after which it becomes the Euler equation, which is reversible. So you have to explain how reversible Euler equation could describe the irreversible process of turbulence. And the thing is, turned out that the microscopic stability leads to boundary conditions for the Euler equations, and these boundary conditions are irreversible. And I will quantify that. Entropy, which is integral of square of vorticity, is conserved as a consequence of another stability equation, that strain times discontinuity of velocity equals 0. And entropy, it's a long-term puzzle, which was kind of a skeleton in a closet of Kolmogorov theory, because the main quantity in Kolmogorov theory is so-called energy dissipation. And that energy dissipation is proportional to entropy. So energy dissipation has to be a constant, it has to be conserved. However, formally in the Navier-Stokes equation, entropy was not conserved. It could be only conserved by some magical cancellation. And we found the origin of this magical cancellation of all the terms in Navier-Stokes equation, and I will explain that later. Stochasticity, which is the mere fact of randomness in a deterministic equation, it is explained in our theory by accumulation of contribution to the background strain from large number of remote vortex tubes, the Biot-Savart law. Biot-Savart law is like electric law, which describes the velocity created by the vortex structure. So if there are many, many vortex structures on the horizon far away, since the Biot-Savart law decreases very slowly, like 1 over r squared, they accumulate, and when you have a large number of random things accumulated, you get the Gaussian random number. And that's what happens with the background strain. And their terms are random because these structures are located at random positions in infinite space, and they kind of contribute like a, it's called late night paradox, large contribution from large number of far objects. And that's the origin of stochasticity. Now, finally, there is a phenomenon called multifractals. Multifractals is something which is more than scaling laws. It's scaling laws with drifting dimension different for every moment of distribution, in this case, distribution of velocity differences. So that is explained as a result of fluctuations of fractal dimension of the surface involved in the CVS solution. So we kind of have qualitatively and sometimes quantitatively explained most of the features. And I'm going to present that solution right now. So our flow is similar to that of the turbulent boundary layer theory, which basically says that there is potential flow except in a small vicinity of the body, which the flow is flowing past. In the small vicinity of the surface, there is a vorticity which is described by the boundary layer theory. And here you have a similar situation, except instead of the flow past the body, it is flow past the vortex tube. And there is another big difference. There is explicit equation for the stable vortex tube, which makes it a random surface with a known distribution of its shape. It's not just any body. The flow in turbulent boundary layer theory could go past arbitrary body. Here, there is only one stable family, actually, of stable shapes of the vortex surface, which I'm going to describe later. There are 4 different scales in our solution. They're all ordered, and at small viscosity, they are parametrically larger one than another. So the biggest scale is L, because our structures are elongated tubes, very like a spike or a needle, very long spikes, and then there is another scale, which is a distance r between these vortex structures, which is smaller than L, and then there is a perimeter of this structure. So there are elongated tubes spaced at very large distances between them compared to their size. And then there's a 4th size, which is the thickness of the skin. These are hollow tubes, and the skin is like boundary layer, has a thickness proportional to some power of viscosity. When viscosity goes to 0 at fixed energy dissipation rate. So that's the hierarchy of scales. And it's not like my fantasy, because all these estimates come from self-consistency solution. It's basically property of solution. It's not like I'm imposing those conditions. They follow from equations. Now, I already mentioned all these things. Yes, these vortex structures are elongated hollow tubes, and the cross-section of the tube is singular. It's made of 4 branches of hyperbola with costs at x equals 0 or y equals 0. So that's how it looks. It looks like a, spaceship. Anyway, so these red opaque surfaces are vortex surfaces, and then they separate the region between from the region outside. So the cross-section of the flow looks like that. So the red line is this. Now we're looking through the cross-section of that. It is a cylindrical symmetry. So there is a flow outside, the clear part, and then there is a green stagnant water inside, or flowing in the opposite direction. If you look at the one quadrant, because they are all symmetric, then there is a flow in one direction outside and another direction inside. On the surface, on the vortex surface, there is no tangent discontinuity, so the flow slides along the surface in both phases. But you know, at the surface, there is no normal discontinuity, but there is tangent discontinuity because it goes in opposite directions at different sides of the surface. Now, the local potential velocity, they're not arbitrary because there are all these CVS boundary conditions, which I'm going to mention later in more detail. So normal component of velocity must vanish. That's one condition, obvious condition. That's condition of stability. I mean, that's condition of steadiness. So the normal component of velocity is 0, and the tangent component means the surface is not moving, but the flow is sliding, constantly sliding around the surface. But normal component is 0. And then there is new condition, which I derived, which is that strain times velocity discontinuity must vanish. So there is no strain in direction of discontinuity. And then the negative, the normal component of the strain, which is this, must be negative. So these three conditions are necessary for stability. And we studied them in separate work. It was published in the beginning of this year. This found exact solutions of the Navier-Stokes equation in arbitrary background strain. And this reference, this one, it is Wolfram notebook. You could find references in my paper. So I do some calculations as a using Mathematica, which is favorite of me and my former student Young. So I have like 4 Mathematica notebooks associated with that paper, so that all the calculations could be verified there. Let me get back. So the solution, the general solution for arbitrary strain is too complex. It is some hypergeometric function with parameters depending on the ratio of 3 eigenvalues of the background strain. But only the degenerate case when the middle eigenvalue is 0 and S dot delta V equals 0 is stable. Others are not. So I'm not describing those unstable solutions. They are studied in those papers. So just to be on record, so you understand, it's not model, it's not approximation, it's exact solution of Navier-Stokes equation in the local tangent plane. And why I'm doing local tangent plane? Because with small viscosity, the width of the boundary layer is small, so you could neglect the curvature and consider the plane locally, the surface locally plane. So here is a solution. It's some generalization of well-known solution, I would say well-forgotten solution of Burgers and Townsend done in the previous century. And it took me, I rediscovered it myself, then I started digging references and found indeed it was their solution. So velocity equals some potential background velocity plus error function of normal direction to the surface times discontinuity of velocity. So this error function approximates the gap. So the gap is represented by some smooth function like error function. And a similar formula for vorticity. Vorticity is just a Gaussian with the width h. And h is very interesting formula, square root of viscosity divided by minus negative component of strain. So strain, negative, normal component of strain must be negative, otherwise that solution would not exist. So that's one of the stability conditions. That's how the error function looks. So it is a gap like step function, which is smoothed on the viscous scale. The width of that interval is h, related to some positive power of viscosity. And now, here's the most interesting new thing for people who studied the turbulence, is this is the famous energy dissipation, viscosity times integral of omega squared. That's exact formula for energy dissipation. And if you find the Navier-Stokes time derivative of that, you'll find it's not constant. Time derivative of that is not 0 in general. What we found is that in case of this vortex sheet, this omega is concentrated around the surface, and this integral over space becomes the integral over a surface with calculable coefficients. So that's what this standard dissipation integral becomes, in case of the vortex sheet, there is square root of viscosity, there is a well-defined coefficient, and then there is square root of this negative component of strain times the square of velocity difference. This gradient gamma is the same thing as velocity difference. Now, if you find time derivative of this thing through the Navier-Stokes equation, you'll find something which is not identically zero. However, what you find in the limit of thin boundary layer, you will find the integral which involves strain times gradient gamma. So if strain annihilates gradient gamma, then the entropy is conserved. That's one more self-consistency confirmation of the fact that this is a stable solution. Otherwise, this thing will not be zero. So this is not an Euler conservation law. I just want to explain to you, people are used to conservation laws, which are properties of the Euler dynamics. Euler dynamics have plenty of conservation law. For example, energy is conserved in Euler dynamics. However, in Navier-Stokes dynamics, energy is not conserved. It's rather dissipated. However, the time derivative of dissipation, turns out, is conserved in Euler dynamics, which is a surprise. This comes as a result of cancellation of various terms like stretching, diffusion, and advection in the Navier-Stokes equation. These terms cancel exactly only on the CVS surface. Otherwise, this will not be conserved, and therefore it will not be confined to the surface. So we found exact solution of these CVS equations to our own surprise. It took us a long time. We made some false start. We used some theorem saying that the Brouwer fixed point theorem proves existence of that solution, but we kind of didn't even hope to find exact analytic solution, but here it is. Here is the closer look at one of the branches of the parabola. So this horizontal direction is z, and x and y is the vertical plane. So there is this solution which doesn't really depend on the z coordinate because the surface is just a parallel translation in z direction. So there is n is normal to the surface, and E1 and E2 are two tangent plane vectors. So one of them is z, another is some combination of x and y, and so is n. N normal vector lies in the xy plane, is just rotated. So that's the geometry. So with this geometry in mind, we have an explicit solution for velocity field. And I apologize, it is more than one formula, because usually you display only one formula on a slide to spare the audience from too much thinking. But I, like my former student said, I'm usually torturing my students, and I'm going to do that today. So here is velocity field. Z component is just linear, but x and y components are part of some non-trivial holomorphic function. So this complex coordinate, x plus iy, so the complex velocity Vx minus Iy is related to complex coordinate x plus Iy through some analytic function. And there are two different analytic functions. One is inside this vortex tube, and that's simply a linear function, very trivial. And another is outside, and that function outside is only known as parametric function. There is new complex variable w, and coordinate is parameterized as w minus iw to the minus mu, where mu is some index. So that's solution of this transcendental equation. Other than that, it's analytical. You could use it as a parametric equation, and you could build the whole velocity field with arbitrary accuracy, which we did. And the curve, which is a boundary between these two solutions, is this hyperbola. It's hyperbola with some index, x to the power mu times y equals constant. And mu, the index, is related to the ratio of eigenvalues of the background strain. And in the moment, I'll talk about background strain and what is the meaning of these eigenvalues. So I already showed you the shape of that flow. It's rather simple. It's not, doesn't have any structures outside. It only has a vortex surface, and inside and outside, it's a very smooth flow, except there is discontinuity at the surface. Now let's study the surface as it is. The surface is infinite length because that's a hyperbola going to infinity. And there are singularities, and the area is also infinite because of these cusps. So at large upper limit and small lower limit, you have two divergences. This integral, which is a perimeter of the curve, diverges. It diverges at small distances, like x minimal to the minus mu, and at large distances as x max. That's what we have here. So if you, in a viscous fluid with finite viscosity, that solution would not be applicable everywhere, because when spacing between these two branches, say at the x equals 0, I mean at y equals 0, at horizontal x, for example, there are two branches, they are approaching each other. So when the spacing between the branches becomes comparable with the thickness, that's when the solution should be modified. It's not applicable there. So there are natural cutoffs of this solution. And if you work these cutoffs out, you'll find that, that for perimeter to stay finite, these parameters are not in front of the solution, should go to 0 a certain power of viscosity. And same thing with area. Area is proportional to perimeter times thickness. So it's quite a singular solution. The parameters have to be adjusted with viscosity. And when viscosity goes to 0, this surface basically shrinks to 0. But at finite viscosity, which we live in and are going to live in the nearest billion years, with finite viscosity, like water, and finite velocities, of course, everything is finite, and therefore these surfaces are not really infinite. What happens is the following. Here is, now I'm trying to explain stochasticity. So here is the blue thing denotes my vortex structure, and the red circle denotes infinity. There are many, many other structures like that in infinity. So each of these red arrows represents randomly aerated and randomly positioned other vortex tube. So they are all at infinity, and they each one contributes to the background velocity, which could be boosted away by Galilean transformation. But then there is background strain, which is really something with physical effect. So this background strain comes from the contribution from all these remote vortex bubbles, which I denote as red lines. So it's integral of the type of the multiple expansion. You could write multiple expansion. It's integral similar to the distribution of the electric field from collection of charges. So B denotes one vortex structure, or bubble, I call it. So when you look at that term, each term decreases as 1 over r cubed, and they could accumulate. And that's exactly the origin of stochasticity. Central limit theorem suggests that strain would be a Gaussian tensor variable, satisfying normal distribution of symmetric traceless matrix with 0 mean. Just because Gaussian central limit theorem says that every component of this, every independent component of this tensor will be Gaussian variable, and of course there is rotational invariance, and therefore there is very well-defined measure which is studied in mathematics, and it's just Gaussian distribution in terms of symmetric traceless tensor. But if you eliminate the rotation matrix, diagonalizing that tensor, then you'll get distribution of eigenvalues. And that's exactly what we are using here, because we are working in a frame where this tensor is diagonal and z direction is directed along its largest eigenvalue. And x and y are in an orthogonal plane. So for arbitrary background tensor, this solution which we described automatically, is aligning itself along the z direction, and then the normal component of the strain will be negative, as it should be. So if we expand this Biot-Savart integral in terms of multiple expansion in 1 over r and taking the leading term, we could now compare the variance of the distribution of that tensor with that coming from the expansion. There is self-consistency equation that same variance can be computed using expansion. So when you compare these terms, you get non-trivial relations between various parameters. I just skipped that part, it's in my paper. So there is a mean distance, which is much larger than a perimeter. So it is proportional to the viscosity minus 3/10. The ratio of length to the radius is viscosity to the minus 9/10. And if you find the ratio of length over square root of area of the cross section, then it goes viscosity minus 27/20, which is totally crazy. And now the ratio of length to perimeter goes to infinity as viscosity minus 6/5. So these things follow from the self-consistency estimate between the variance and the energy dissipation. Now we can make some predictions. If you have a theory, it should predict observable things. And here's the first observable which we can predict. We consider the energy dissipation and actually compute that energy dissipation integral for our solution. When the dust settles, if you just compute that and use the random matrix distribution, you get universal distribution for this scaling variable. Scaling variable is energy dissipation divided by some combination of lengths and parameters. And that, of course, should be of the order of 1. Its expectation value is 4.9. And that's this interesting formula, which, of course, can be plotted. That's how it looks. It has a Gaussian tip, but then it has very different asymmetric tails on the left and on the right. So I would be very interested in comparing that with experiment. And now, the most exciting part of our theory is multifractals. Multifractals. So our hyperbolic vortex tube is smooth, but its shape, governed by the index mu, is fluctuating. This index is fluctuating because mu is a ratio of eigenvalues, and eigenvalues are distributed. Now, fortunately, this ratio of eigenvalues is distributed in a finite limit. Mu is distributed between 1/3 and 2/3. That's a property of this von der Monde determinant. So fluctuating power indices imitate what is called multifractal. There are no actual fractals present. It's just the smooth surface with statistically distributed parameter in its power. And if you compute perimeter, if you compute mean distance between points on that surface and find how they are related, you find d log p, d log delta r, you'll get this. So you'll find that it's called fractal dimensions. I didn't invent that word. It is definition of fractal dimension. However, this definition was kind of designed for something wavy, fuzzy, not like smooth surface. So if you have a smooth surface with distributed shape, it also have a fractal dimension. And this dimension is not constant. It is distributed between 1/3 and 2/3, and here is this density. That's density, universal density, which you compute from that thing. And that's how it looks. It goes to 0 at 1/3, goes to 0 at 2/3, and it has a peak somewhere in the middle. It's symmetric. And if you have the object with fractal dimension, which is fluctuating, then of course you will not have the power laws. If you have the object with fixed fractal dimension, then you could expect the power laws for observables. But if that fractal dimension is fluctuating, then of course the laws observables will be more complex. And here's what happens with these observables. The most interesting observable is velocity difference. You take 2 points in space and find the difference between velocity in these 2 points, and you see how they that expectation value of moments of powers of this velocity difference scale with the distance. And in Kolmogorov theory, they should scale as distance to 1/3 raised to the power n. So nth moment will be r to n/3. And that's not what is observed. What's observed is more complex curve. Now let's see what our theory says about that. So velocity difference between 2 neighboring points in the potential flow scale as R1 minus R2, because harmonic potential has no singularity. So if these 2 points happen to be in the potential region of the flow, in that case, there will be no non-trivial index. It will be just linear. It's not what to observe. So only situations when these 2 points are on the other different opposite sides of the vortex sheet contribute to that anomalous scaling. And with our probabilities, these points will be separated by vortex surface. So here's how it looks. That's a piece of the vortex surface. That's the outside region. And this is inside region. And these are these 2 points separated by fixed distance. So if you fix those points in space, then the surface would simply fly all over the space, keeping these 2 surfaces, these 2 points on different sides. So if you go to the frame where the surface is fixed, you would let these two points just slide along the surface, keeping fixed distance with them. And since the surface has a fractal dimension, which is dependent on ratio of the eigenvalues, you will have similar scaling laws, non-trivial scaling laws for the velocity difference. And what you will have is something horrible like that. You'll have integral over rotations. You will have 4-dimensional integral over coordinates. And then there will be velocity difference, which explicitly depends on this delta r. What is clear looking at that function is that it is a non-trivial function of both variables, n and delta r. It's quite an undertaking to compute it, and I haven't done it yet. However, what I did, I found the estimate. It's very easy to estimate it using the following simple observation. In a recent work of Srinivasan and Yachot, it was argued that with the renormalized Bernoulli formula for the pressure, so if you say that pressure is not just minus 1/2 v squared, like in Bernoulli theory, but some coefficient times this. So they arrived to this model saying that this coefficient comes from what they call turbulent viscosity. They could have that if you normalize Navier-Stokes equation and replace actual viscosity by something which is partly coming from the fluctuations around the it's renormalized coefficient. And then they would say pressure would be some coefficient times v squared. That, of course, is a model, but model with good physics behind it. So in their theory, this coefficient was explained, it's less than 1. It was, this deviation from 1 was coming from turbulent viscosity. And once they assume that formula for the pressure, then they could close the chain of equations for the moments. You know, if you take Navier-Stokes equation multiplied by nth power of velocity and then expand, you will obtain infinite chain of equations, which never close, of course, because there is pressure, and pressure in general is non-local functional of velocity, and you really don't have closed set of equations for moments. However, if you make a small sin by replacing pressure by something times v squared, then you could close this chain of equation, and you get something which is relation for the moments, which is very close to experiment. So they got some formulas, which they interpreted as formulas for the so-called fractal dimensions, which it is not, because there is no exact law which will say that this difference in scale is some power of R. But anyway, what they observed is that with alpha 0.95, they have pretty good explanation of the experimental facts. And in our theory, that makes a lot of sense. Because look, the majority of points in space are outside the vortex surface. And there, of course, original Bernoulli formula with alpha equal 1 holds. So if we just neglect the thickness of the vortex surface, then we would assume that probability of having no vorticity at given point equals 1, because the surface has dimension of 2, and our space has dimension of 3. But as we know, it's not quite true, because the surface is fluctuating, that's fractal dimensions not equal to 2, etc., etc. So if you take all that into account, you could explain alpha less than 1. You can't explain alpha more than 1, but you could explain alpha less than 1. Because then you say, okay, this alpha is just a probability of having no vorticity at given points. And if vortex surfaces have a finite thickness, then roughly speaking, this probability is below 1, and the difference is just the volume occupied by the surface compared to the volume occupied by the region we are studying. So yes, you could explain with finite thickness, which is h, which is inversely proportional to so-called Reynolds number, to 1/2. Then you could say, yes, for finite Reynolds number like 10 to the 4th, you have this thickness like 10 to the -2, and that is what we have in this coefficient. You see, this coefficient is 0.95, 5% less than 1, so that all matches. So, of course, we have to compute that integral and actually find the function. And of course, it's not going to be pure power, even for fixed n. The difference, velocity difference generated by this fluctuating gap will not be pure power, but it's calculable. It's just a, I don't know, 9-dimensional integral. It's something much simpler than solving the whole Navier-Stokes equation. It's something which could be computed, and that's what we're going to do next. So let me get back to the summary. So we found the solution of Navier-Stokes equation. This solution have few stages. There's a macroscopic solution, which says that most of the space is pure potential. Then there is a next hierarchy level, which says that those small areas where there is vorticity, those are very special singular surfaces satisfying the stability equation. And we found the shape of these surfaces by explicitly solving the stability equation. Now, the stability equation comes from these two relations. For local normal strain, it must be local normal strain might be negative, and local tangent strain should be orthogonal to the tangent discontinuity. And these conditions are sufficient to find the solution. Now, these conditions follow from the exact solution of Navier-Stokes equation in the boundary layer, which we also found. So this general solution shows that only given these conditions, we have stable solution. Other solutions are found. They have hypergeometric functions, but they are not stable. So only this one is stable. So we have sort of exact solution of the whole Navier-Stokes equation, except it's not a whole complete formula in all scales. It is 3 stages. It's like pure potential in the space between vortex structures. It is this flow around the hyperbolic shape, which is analytically known as a parametric equation near the structure, and then it is this general error function in the skin of the surface. So we have 4-stage solution, which is a attractor, and we have the physical meaning of this physical explanation of the stochasticity. those instabilities relate to the simple fact that each vortex structure has a very long tail influencing other structures via background strain. And if you add large number of these randomly located vortex structures, they contribute to a large number of tensor terms, which describe through the central limit theorem, they are described by the Gaussian distribution. So that's the origin of instability. Just because there are many other vortex structures, naturally they create self-consistent background strain, which is distributed like a Gaussian random matrix. And then we just apply the theory of random matrices, which is my favorite subject. Now, multifractals are not completely explained. We just have the general formula and some heuristic arguments, but we see the phenomena of fluctuating fractal dimension of our surface. And that is a phenomena which is responsible for this multifractal non-trivial distribution of moments. So that basically is my talk. And I would really, if I have some more time left, I would like to hear any questions, criticisms.
Hello.
Great.
Yeah. So great. Thank you very much for that really nice talk. To be honest, since being exposed to Navier-Stokes by you and by Professor Polyakov as an undergraduate, I haven't thought about it at all. But now your talk is reinvigorating me. So please, are there any questions from the audience?
I had a question. Hi, Sasha. This is George Minich. It was wonderful and really exciting what you're doing. I just wanted to ask you two things. First is in 2 dimensions, right? If you just do everything in 2 dimensions, right, you have conservation of entropy. So I'm just wondering, how does your solution looks like in that case? You must have thought about it. And the second most obvious question is, you have done this loop equation business, right? And that was very beautiful. In turbulence, where the Kolmogorov scaling was e to the minus area of light of the loop 2/3, and for Kraichner you can even get the area law. So what does this mean from the point of view loop equations?
Okay, first of all, let me answer the first question.
Yeah.
Unfortunately, in topology, odd and even dimensions are not analogous. So the close relative to the 3-dimensional Navier-Stokes is 1-dimensional Navier-Stokes. And that is studied. There is a Berger's equation, and there is a well-known phenomena of shocks. Shocks are analogs of my vortex surfaces. They are exactly the same thing. So in Berger's equation, it is known that you could describe the physics of the Berger's distribution either by, in terms of fluctuating velocity field, and you could compute the tails of distribution like we did with Gurari and others. In terms of the wild integral for the velocity field, so that is the field theoretical approach. But then you could also compute the physics of the, statistics of the 1-dimensional Berger's theory in terms of the shocks, and it is a dual description. So what I'm doing here is similar thing. Instead of describing fluctuating velocity field, which is hopelessly complex, I'm describing fluctuating of the surfaces, which are in the extreme turbulent limit, the surfaces are not so complex. It is similar to the duality between the conformal field theories and string theory. So the theory of fluctuating vector field is dual to the theory of fluctuating geometry, and the strong coupling region of the field theory is equivalent to the weak coupling region of the fluctuating geometry, like string theory. So that's what I'm doing here.
Okay, I'm getting it. Yeah, okay, thanks. I think
now regarding the loop equations, loop equations made a long evolution since those papers you mentioned. Indeed, the area law was one conjecture, which is approximately true, but in the closest look in the recent papers a year ago, there are modifications of that conjecture. the thing which was more or less established with loop equation is asymptotic saturation of indices, is that at large areas, the tail of distribution for the velocity circulation has the index alpha equals 1/2, meaning that the mean vorticity is like square root of area, and
Okay.
that indeed is confirmed by the classical solution. I did some work last year where I studied asymptotical distribution of the Wilson loop in turbulence, and I found some classical solution, which is not this. It is different classical solution. It's classical solution in 3 dimensions, which has topological properties of so-called Alice string. It's the classical object, topological object studied in the theory of gravity, string theory for the universe, and also studied in the liquid helium, which is example of the zero viscosity fluid. So I found that there is a solution with that properties, with this non-trivial topology. It's a surface bounded by a loop, and that solution explains tails of distribution, which was measured by Srinivasan and others. So there is a different kind of activity which is tangentially related to the loop equations.
Okay, thank
Loop
you so
equations
much.
may be beautiful, but they unfortunately don't let you find exact solutions. Turns out that this turbulence problem is much simpler than QCD. My basic message today is that Navier-Stokes turbulence is less than a field theory. It is theory of random surfaces with finite dimensions, not infinite dimensions. It's not two-dimensional, it's zero-dimensional theory.
Yes, I think I got that point. Thank you very much. Okay, thanks again.
You're welcome.
Thank you very much. I think we're actually exactly on time, being in the sense of 7 minutes before we started 7 minutes late. And let's thank Sasha again for his nice talk.